All right, so welcome everybody. It's January 5th. Happy New Year to all. And Leonardo Biagioni, thank you so much for being with us on this, first week of January. Looking so forward to hearing your presentation. You're with Fusion for Energy. You're the Deputy CFO there. I'll give you a proper introduction after we let people settle in a little bit. So just to bridge that time, I'm going to go ahead and share my screen and play our video and just introduce FrontierDAO a little bit.
FrontierDAO is a decentralized autonomous organization focused on scientific and engineering innovation. It is one of the first DAOs focused on scientific pursuits, hence one of the pioneers in DeSci, decentralized science. As a collective, FrontierDAO's main mission is to make scientific research, collaboration, innovation, and commercialization more accessible to wider groups of people, regardless of where they come from. Our philosophy, echoing that of NASA's, is that good ideas come from everywhere, and we are using the blockchain and Web3 tooling to help facilitate that people with good ideas, drive, and determination get access to funding, mentorship, peer support, and paths towards collaboration and commercialization, while still protecting their IP. FrontierDAO is committed to creating public goods by leveraging emerging technologies to benefit every human being on our planet. Catalyzing space and fusion technology incubation, FrontierDAO is working towards the vision of clean energy democracy. That is, clean, cheap, abundant, on-demand energy for all. By facilitating multiple pathways for funding for fusion energy innovation, FrontierDAO aims to collectively help make clean, affordable, and accessible energy available for everyone on the planet. We aim to do this by supporting paths to commercialization of this new technology, while still protecting the rights of the inventors and researchers to ultimately create a more vibrant, abundant future on this world and off-world that is shared more equally by all. FrontierDAO's work to support research as well as inclusivity in science, engineering, and the aerospace industry includes adopting space technologies to earth sciences to improve the quality of life on planet Earth as we simultaneously reach for the stars and become a multi-planetary species. Visit frontierdao.xyz today. If you have questions or would like to know more, feel free to reach out to co-founder Paige on LinkedIn.
Okay, so welcome again, everybody. And interestingly, in that presentation video, you saw sort of a correlation between fusion and the space exploration and space technology. And there is such a great relevance here today with that because Mr. Biagioni has a master's of science in aerospace. So he's actually a trained aerospace engineer who found his way into a career in fusion energy. So it's interesting how there does seem to be a very strong link between the two disciplines. Also, I'm gonna let you, Leo, tell us a little bit about your background, how you came to fusion energy, and a little bit more too about fusion for energy. You explained it to me really great in an email that how fusion for energy is kind of like the Department of Energy, and Eurofusion, whom we featured on this workshop a couple months ago, is more like the National Science Foundation. Or do I have that the wrong way around? Can you tell us?
No, it's correct. And thank you, Paige, and good morning, good afternoon, good evening to all those who are attending, depending on where you are. It's evening for me in Barcelona, in Spain, but I think it's probably early afternoon or maybe even evening if you're on the East Coast, late afternoon, evening. So yeah, that's more or less how you can see the picture. I have somehow this explained in the slides I've prepared, but that's correct. Fusion for Energy is taking the same role that DOE is taking in the US, whilst Eurofusion is engaged more in basic research activities, engaging with universities, research laboratories, public research laboratories in Europe. So maybe I can start with my slides.
Well, and tell us a little bit about your background, how you directed your career towards fusion energy. It's fascinating.
Yeah, I mean there was no specific plan or strategy. It just happened. But yeah, I mean, careers develop in strange ways, and that was also the case for me. So maybe I can start then with some slides. I will try to be a little bit to be going quickly through the slides so that we have time for discussion. The objective today for me is to tell you more or less what is happening in the development of fusion energy, seen from the European point of view, of course. There are many things happening worldwide, and the different actors in the US or China, Korea, Japan, Russia, India, they're doing things in slightly different ways. In Europe, the development of fusion energy is really at the moment going through the construction of the ITER tokamak, and we'll explain to you a little bit where we stand with ITER. And then I will conclude the presentation asking the question, quite fundamental question, if the development of fusion as an energy source can be accelerated, and in particular, if it can be accelerated through synergies between public and private funding. But okay, let's start from what Paige was mentioning a few seconds ago. I'm an aerospace engineer. And then after my master's, I got a PhD in plasma engineering. I worked before joining Fusion for Energy, and I will tell you in a second what Fusion for Energy is, with space agencies in the US and Europe, and then with a space startup at the beginning of the new century. So, getting back to how Europe is undertaking the development of fusion technology with the objective then to turn fusion into a sustainable source of energy, there are essentially two pillars in the European Union architecture for fusion. There is a pillar which belongs to the research and innovation family of the Union. This pillar is Eurofusion. Eurofusion is an organization coordinating all fusion research in public labs and academia. Fusion research in different directions, different technologies, magnetic confinement, of course, that's where Europe is investing the most, but also inertial confinement and also more exotic technologies. And then there is, let's call it an industrial actor. An industrial actor in the sense, an organization which task is to turn the technologies, to industrialize the technologies which are developed by the research community. This belongs to the energy part of the European Commission, the Energy Directorate General, and this organization is Fusion for Energy, the organization where I work. So Fusion for Energy, or FRE in short, is the European Union agency for ITER and the development of fusion energy. We are based in Barcelona, where we were set up in 2007, but we have other sites in Europe, but also outside of Europe, in particular in Japan, due to a a specific bilateral collaboration agreement between the European Union and Japan on fusion technology. There are four main projects in which FRE is engaged. The most important one at the moment is ITER. ITER is ITER is an acronym which stands for International Thermonuclear Experimental Reactor. It's the largest magnetic confinement fusion machine ever built, which is under construction in Europe. Europe is the main contributor to this project, and this contribution comes through Fusion for Energy. Then there's other activities, as I was mentioning, that we perform in collaboration with Japan. All of these form part of a program which is called Broader Approach. It comprises building together with Japan the smaller tokamak in Japan, building a research installation for testing materials exposed to a fusion environment. It involved a supercomputer which was installed in Japan as well, and other activities. Then a third project which is going to be very important for us during the 2020 decades is the full-scale material testing facility, which prototype was developed within the Broader Approach program. This is called DONES. It's an installation producing neutrons similar to those generated by a fusion reaction, and testing materials under being exposed to such neutron flux. And then we have a fourth project, which is the early activities, the early design activities, early prototyping for demo. Demo is the step which will come after it, which is planned to come after ITER on the path for magnetic confinement fusion. And it's ideally at the moment it's foreseen to be an electricity generating fusion installation. ITER is not generating, it will never generate electricity. ITER will generate thermal energy, heat, which will not be transformed into electricity. But demo will have this task of generating electricity. So I assume you are quite familiar with fusion, else you probably would not have joined tonight, but in the sun and all the stars. It's a process through which energy is generated not by splitting atoms, as in the case of fission, but by merging together atoms. And in both cases, both in the fission case and in the fusion case, there is a mass change in the process, and this mass change is transformed into energy following the well-known, famous or infamous, depending on how you see it, Einstein equation. A lot of energy is generated during fusion process because the mass gap, the mass change, is larger than in the case of fission. Why fusion energy is attractive? Why are we spending so much time and investing so much effort in developing technologies for fusion energy? So fusion energy is kind of a holy grail for energy generation. It's a source of energy which uses fuels which are plentiful and available all over the world, does not emit greenhouse gases, and in terms of safety, it's a safe nuclear reaction. There's no generation. If you have a properly designed reactor, there's no generation of long-lived radioactive waste. So the radioactive waste is short-lived and relatively easy to manage, and there is no risk of getting to an out of a meltdown situation or a reactor running out of control. The energy density, as I was mentioning, is very high, and the type of fuel which is used for fusion reaction is also available, plentiful over the world, all over the world. If you just look at how much energy can be generated by fusing or by using in meter like tokamak 50 grams of lithium and 12 grams of deuterium, this is generating the same amount of energy as burning 300 tons of oil. And this is the total energy which the average EU citizen consumes during the whole life. Clearly, deuterium from seawater and lithium from earth crust are really available in large quantities, which means that energy would then become, I wouldn't say a commodity, but it much more accessible resource to have any citizen, any human being. Fortunately, it's not easy to have a fusion reaction on Earth. If it were easy, we would already have it in practice, and probably these internet connections would be powered by fusion energy. But it's not easy, and it's many years that a lot of brilliant people are working on it. The issue with the fusion reaction is that in order to have a generation of energy through fusion, you need to fulfill simultaneously three conditions. You need to have a temperature which is high enough to bring together the different nuclei, and we will see which nuclei we're speaking about, and fuse them together. We need to have a sufficient density of this high temperature gas, which is a plasma, because at this high temperature it's ionized. And we need to be able to maintain these conditions for a time which is long enough for the fusion reaction to occur. These three conditions together are called the triple product. So when you look at the performance of a fusion machine, very often this is expressed in terms of the value of the triple product. In the sun, the reaction which is occurring is a reaction between protons and then between hydrogen, deuterium, hydrogen isotopes. And this is going on, all of this is just kept together and compressed by the sun gravity. On Earth, we cannot achieve the same type of situation as occurring on the sun. Therefore, the proton-proton fusion, which is the main process, the main source of energy in our sun, is not feasible. So on Earth, what we try to achieve is a deuterium tritium fusion. So we try to fuse two different isotopes of hydrogen because they have a much larger collision cross section. So it's much easier that you get to a fusion, a successful fusion process between these two ions. So the triple products, the simultaneous combination of temperature, density, and time can be achieved in different ways. On the sun, this is achieved by the gravity. So we have, say, a gravitational confinement occurring in the sun. We have a high density. We have an ultra-large scale, a very large volume of space, which is occupied by these plasma, in which these fusion reactions take place. And the sun and the containment, the time over which this plasma is contained is very long. Now, clearly, this is not practical for for reproducing the fusion reaction on Earth. So on Earth, essentially, there are two different ways of achieving the triple product. One, which received a lot of attention at the end of 2022, is inertial confinement. In inertial confinement, you try to achieve a very ultra high density in a small volume over a short duration of time. So you probably read in the press the announcement, which was released by the NIF in December, when they achieved ignition. So they achieved for the first time a situation through inertial confinement in which more energy was released by one of these laser pulses. More energy was produced and released than the energy which was beamed onto this fuel pellet. Another way to achieve a fusion reaction is through magnetic confinement. Magnetic confinement is an approach in which you have a relatively low density, but you keep it for a longer time and on a much larger scale, several meters or tens of meters. Magnetic confinement, in a magnetic confinement case, the triple product is achieved by having a temperature in the order of 100 million degrees at a pressure which is in the order of 2 atmospheres for a time which is in the order of 5 or more seconds. So when you can achieve these three conditions in a magnetically confined plasma, then you achieve a triple product which corresponds to the plasma ignition. The way in which this is attempted in most laboratories and most countries in the world is through a device which is called the tokamak. Tokamak is a Russian acronym, and it means toroidal chamber with magnetic coils. Essentially, this is, as you've probably seen it in many pictures, it's a donut-shaped vacuum vessel with several very powerful magnets, which are keeping these ionized particles away from the walls. And inside this donut, you have the plasma generating fusion. I would say that, at least in Europe, magnetic confinement is considered to be the most promising way to get to fusion power generation. And this is believed because there were, since the 60s, in fact, many different tokamaks that were built and showed increasing performance. And all of this know-how then converged into the latest generation of the tokamaks, which is represented by the ITER machine. Performance has improved in tokamaks very significantly since the early experiments. You can see that from starting in the 60s, there were several orders of magnitude of increase in the triple product. And now for ITER, ITER was designed to achieve this DT break-even, so the same amount of energy used to heat the plasma then being produced, being released by the fusion process, which is referred to as Q equal 1. Q is the ratio between the energy input and the energy output, but ITER is designed to achieve Q10, so to achieve 10 times more energy than the energy which is input in the plasma. In this chart, you see, let's say, the public funding undertakings in magnetic confinement fusion, which are the red dots. You also see that starting around 10 years ago, there were several privately funded magnetic confinement fusion machines that have been progressing very quickly and are now becoming really significant actors in the field of magnetic confinement fusion. So Europe has a long experience in magnetic confinement fusion. The JET is Joint European Torus, which is operating in the United Kingdom, is running since 1983. And JET has achieved very high Q, so very high ratio of power input to power output, 0.6, the peak. This was achieved in 1997, and then in the following experimental campaigns, JET also achieved much longer duration of pulses, but with a lower Q. Now, for what concerns magnetic confinement, the next step is ITER. ITER is a very large tokamak, which objective, it's 30 meters diameter, and its objective is to achieve, let's say, a burning plasma, so a plasma which in which you have a fusion reaction with, as I was mentioning, Q in excess of 1 up to 10. And to be able to run this process for a very long period of time. Very long period of time, still being an experimental device, means in the order of thousands of seconds, up to 1 hour. ITER is a very large project, which is comparable in terms of total cost to some of the largest science and technology projects in the past centuries. Impressive machine, very complex, very large, a lot of machinery. And the objective purpose for ITER is being able to release fusion energy for the first time on a large scale for a long duration of time with a high Q factor, and then testing, using these as a test bed for testing key technologies that future fusion reactors, including demo, which is what Europe is foreseeing, that future fusion reactors will use. ITER is an international project. It's the ITER organization, which is physically building the machine in southern France, is made up by 7 parties, the European Union being the host, but also the US, India, China, Korea, Japan, and Russia. And these parties represent more than 50% of the population in the world. So it's really a global project from any point of view. The way in which ITER is built is not by giving money to this ITER organization in Cadarache in southern France, but by providing the components which are then assembled in Cadarache. Europe is providing 45% of the components to the machine. All the other parties are providing around 5%, in fact, 9% each. And you can see how all of these components coming from all over the world then converge on a single site. I will show you a few pictures later on, converge on a single site to be assembled into this huge machine. I mean, for the sake of comparison, you see in the lower right corner, there is a small person, just providing a reference for the scale of the machine. Where do we stand? Because that's one of the questions we often get. So ITER is late. Clearly, there's no doubt. It was supposed to become operational in 2020. It did not. And it's probably going to become operational then at the end of the 2020s. We have several years of delay at the moment. But the work is progressing constantly. This is a view of the site in which ITER is being built. It's in Provence, about 40 kilometers north of Aix-en-Provence. It's a very large site. You can see the civil works. Most of the civil works were completed. Please note that ITER is considered by the French regulator a nuclear installation. Therefore, the ITER site is a nuclear site. And this means that everything, including the civil works, has to be built according to very stringent regulatory requirements. But the civil works are, I wouldn't say complete, but they're for the majority complete. The components have been delivered and are being now assembled inside the tokamak building. The tokamak building is the tall building you see at the center, well, slightly on the left of this picture, the tallest building on the site. Here you see the cryostat being lowered in the tokamak building. This is a component produced by India. These are the large magnets, the large superconducting magnets keeping the plasma in place. The picture is a European magnet, but there are also Japanese magnets. Allow me a little bit of focus on the European contribution. This is another European magnet which is being lowered. It's one of the toroidal magnets. These were produced on site because they're too large to be transported. Here, what you see in this picture is the internal part of the tokamak pit, and you can see a vacuum vessel sector being assembled. This specific sector is produced in Korea and was delivered to the site about 1 year ago. And here you see, for what concerns the European contribution to ITER, where we stand. We have, as I said, almost completed the buildings. The buildings, civil works are almost 100% under European responsibility. We are going to deliver in 2023 the last toroidal superconducting coil, and in 2024 the last colloidal superconducting coils. And we have already delivered other structural components, pre-compression rings as structural components keeping the magnets together. For the vacuum vessel, we will deliver next year the first European sector. The first Korean sector and the second as well have already been delivered. The first European sector will be delivered next year. And we have as well completed the cryo plant, or the liquid nitrogen part of the cryo plant is a European responsibility. Now, all of this is it's trying to just give you the picture of what is happening around ITER. ITER being the most significant, worldwide most significant step to achieve fusion energy. But then a question which comes naturally when you look at the dates on this slide, and you see that, for instance, the DT phase, so the final phase for the ITER machine, is actually coming in the mid-2030s, which means that we will not have a final answer about the sustainability of the economic sustainability and feasibility of the deuterium-tritium fusion reaction until the mid-2030s, or probably late 2030s, which is more than 15 years in the future. So the question which comes almost naturally is, why is it taking so long, and can fusion development be accelerated? Now, in short, yes, it can be accelerated. There are many challenges, technological ones, organizational ones, and we often, when we discuss with the other ITER parties, when we discuss about the situation on ITER, we always come to the conclusion that the largest part of the delays in the ITER construction are not due to technological difficulties, but are due to the organizational difficulties which we are facing in managing such a distributed project with so many parties, with so many cultures, all working together. But still, and we can, of course, argue that public funding is not the most agile and not the most efficient way of building large technologically challenging infrastructure, and I'm the first one to agree on this point. But still, something can be done and should be done to accelerate the development of fusion technologies, because this type, fusion, I didn't get into the details of how fusion fits future energy scenarios. But in any case, a source of energy which is potentially so attractive in terms of availability, in terms of low environmental impact, in terms of scalability, clearly would check many boxes in terms of the energy challenges which mankind is facing. But the question is, point is that, and I think it's a sobering reality, is that even though these are large projects and these are large infrastructure, scientific research infrastructure, investment in fusion, both public and even more so private, is still low. And it's well below, let's say, the critical mass which would be required to really move from an essentially a research environment into a fully industrial type of situation. The present funding mix, which is 90% public, 10% private as an order of magnitude, is not efficient. It's not the most efficient. Public funding is good, is needed, but is not allowing, public funding is intrinsically risk averse, which means that all of these projects follow a very sequential logic in which first you do things, you demonstrate it, and when we're sure that we have removed all the risks, then we move to the following steps. And putting everything so much in sequence means that times stretch very much into the future. And every time you have a delay on one of these steps, everything moves further in the future. And we're facing all of these difficulties, and there's still many questions that need to be answered, and we need to find a way to start addressing these things in parallel. So to look at different things in parallel rather than in sequence, with the understanding and the acknowledgement of the fact that some of these parallel undertakings will result in failures, but also with the realization that we learn from failures almost as much as we learn from successes. So failures are not bad. They're just a way to learn what doesn't work. So we have to find this way to put more things in parallel. At the moment, there's no parallelization. Everything is just waiting for, everyone is just waiting for ITER to be complete. Now, this means, well, this sequential approach is driven probably, yes, by risk aversion. Second, by the amount of resources or financial resources available. And here I'm just showing a chart which was produced by the DOE in the 1970s, showing the level of funding which would be needed. This, keep in mind, this was produced in the 1970s, so around 50 years ago. And this was the level of funding which would be needed in order to come to a fusion reactor, following different strategies. You know, the fastest possible strategy, or fast strategy, aggressive, moderate, whatever. And you can see that the fastest possible strategy required, in these DOE projections, required around 9 billion of peak funding, of peak annual budget, not a constant budget, but the peak budget was in the order of $9 billion. And would have produced, in the planning by the DOE, would have produced a fusion reactor in around 15 years. Lower level of funding would produce fusion reactors later. So the moderate funding, which was only having a peak budget of around 4 billion, would take around 30 years to produce a fusion reactor. And then you see there is a red line in this chart, and this was the 1978. So basically the idea was, if we keep the funding constant at the level which we had in 1978, then we will never get to a fusion reactor. This was the fusion never scenario, in which you just keep running the existing machines, but you do not have funds to invest in developing technologies. Now, the reality is that the actual funding was even lower than that. So the actual funding that went into fusion in the US was even lower than the fusion never scenario. And for reference, this is the total ITER funding, which is a large portion of fusion funding today in the world. It's around 2 billion per year in total worldwide, starting around 2010. Still significantly lower than this maximum effective effort, so the fastest possible path to a fusion reactor. So clearly, fusion funding is low. All of this was a vision developed in a context in which the only funding going into fusion was public. Now the question would be, since around 10 years, we have significant inflow of private capital. So is private funding, can private funding fill in the gap? So bring us to the level of funding which the DOE around 50 years ago estimated would be necessary. And unfortunately, the answer at this moment in time is no, it cannot. If you look at the private funding going into fusion companies or fusion undertakings, you can see that we are in the order of a few hundred millions per year. I think 2021 was a pretty successful year. 2021 and 2022 were pretty successful years for funding, private funding in fusion companies, but still in the order of hundreds of millions. So there is still an order of magnitude between what is going at the moment, factor 10, between what is going at, from private undertaking at the moment into fusion projects and what would be necessary to fill the gap. Then the next question which can be asked is, but can we afford? Can mankind afford to invest more in fusion? I honestly, I don't know, but I cannot avoid to observe that there are some private companies which are making enormous profits, which could fund many times over projects with the same size and same ambitiousness as ITER. On a typical year, Apple generates profits which can fund 29 times over ITER. Shell can fund around 8.5 ITER. ING, which is a large European bank, can fund 3.5 ITERs. And as we are often mentioned, is this, can we afford, or is this luxury? Well, a luxury company, and a luxury good company, LVMH, generate profits which can fund 2.5 ITERs. So clearly, the economy can sustain investments of the ITER side many times over. So it's not a matter of whether we can afford it, but it's a matter of deciding that it's important enough to invest significantly more money. And then when we look at the different view of a different way of looking at funding going into fusion research or fusion development, we can compare how much goes into fusion development with what the GDP of the underlying, what is called underlying GDP. So the GDP of the countries contributing to this research. And here we have on this chart a view of two other large technological projects in the past, in the 20th century, Manhattan and Apollo. Both of them run in the US, clearly in a different context. I'm not luckily, the context in which ITER is being developed is, in terms of geopolitical situation, not the same in which the Manhattan Project was developed, or even in which the Apollo program was developed. But still, if we compare these two large technological projects and how much they how much of the GDP went into this project, we see that at their peak, these projects were taking around 0.5% of the GDP in the US, the underlying GDP being the US GDP at the time. This data, the data for Manhattan and Apollo, was produced by the General Accountant Office, the DAO. And for ITER, for Europe, and Europe is at this moment the group of countries, the European Union is the group of countries investing the most into fusion. We see that for ITER, it's the fraction of GDP going into fusion development is 2 orders of magnitude lower, is less than 0.01% of the EU GDP going into ITER, and in fact around 0.007% being the total average EU fusion funding. So this clearly shows that it is possible to imagine a future in which both public and private entities invest more in fusion, with the effect of accelerating the development by doing things in parallel, by doing things in different ways. And this is one of the themes which is really very very present in the debate around fusion development at this moment in time. How to put together these two sides of fusion funding, the public side and the private side, and how can these two ways of developing fusion work together. And here I'm concluding with this artistic the representation of more or less what is understood at this moment being the situation, and how the public and private undertakings can coexist. Here, what you see is with, let's say, time axis going from left to right. At this moment in time, the majority of the funding comes from the public. There is some private funding, and it's not absent, but it's a minority. It's a situation in which there is still a relatively high risk in developing fusion technologies. So I would say it's understandable that the majority of the funding therefore comes from the public source. It is also accepted generally that some specific technologies can be developed in a private undertaking with the benefit of having a faster de-risking, so a faster reduction of the risks, faster development, and then this faster de-risking can be again re-injected into the public mainstream, let's call it mainstream, with a progressive reduction of the risk for all of these technologies, and then the more the risk is reduced, the larger would be the private engagement in fusion, because the risk profile would be lower, and then at a certain moment in time, the risk would be low enough for some private entity to take over a full responsibility, and then for the public funding, let's say, to reduce significantly, maybe then starting to look at next generation technologies or whatever. And then finally getting to commercial exploitation, which is not for the public, clearly. It's not for governments to do this. At least this is the Western view, I would say, that Europe, US, Japan, Korea, well, I'm not sure about Korea, but definitely Europe, US, and Japan, this is the understanding that at a certain moment in time, private operators would take over. And this is the debate at the moment. Fine, this concludes my presentation. I'm just putting my email address on the screen. If you want to reach out and keep interacting or discussing, please feel free to write me at the address there. And well, I think I can stop here, and we can see if there are any questions or comments. I hope I provided a clear view of the status of the debate, at least, as I said, in Europe, and this is the European point of view. It's not the same everywhere.
Leo, bravo. That was really a great presentation. So every year Apple makes enough profits to fund 29 ethers?
29 yearly ether budgets, and it's not 29 ethers as a whole project over spanning 25 years, but it's 29 times the yearly budget going into ether.
Wow. That would be, I mean, that's impressive. That would be 1 ether in every European Union country plus 2. That's
yes.
Oh,
which
that's
is fine, because as you know, I mean, ether is built by Euratom, which is not only European Union, because Switzerland is also a member, and well, we hope soon the UK will be again a member, which brings the total to 29.
Oh, there you go. Well, listen, I know there was really great interest. I couldn't monitor the chat too much during your presentation because I was so riveted to what you were saying. But I think Eric had a question. Eric, do you want to unmute and ask your question? Yeah, please.
Sure, thank you. So I noticed on your timeline, thank you very much, Steve, for your presentation. That was fantastic, very interesting. So I noticed on your timeline, about halfway through, there was a timeline of structural build, and then once that came to an end, in not so many years' time, by the looks of it, from what I remember, then there was about 10 years or so where you sort of from where first plasma was created through to when it was expected that, you know, hopefully fusion power would be done successfully. I was wondering, the time, obviously, it's quite clear to see how extra funding would support the build, speed up the build process. And perhaps it's obvious how funding would speed up the practical fusion process, the practical element of actually implementing ITAR. But could you clarify how the funding would actually speed up the practical process of the experimental sort of stage to try and fast forward the 10-year gap after structural build through to hopeful successful fusion reaction, sustainable fusion reaction?
Yeah, I apologize, maybe I was not clear on this point. I'm not saying that additional funding will accelerate significantly either. Probably even, you know, pouring money on Ether would have a relatively small impact on the time to complete and on the time to achieve DT. There are many constraints, some of which are purely regulatory. I'm not saying that they're less important, but they're not technological. What I'm saying is that we should not wait for Ether to be, for the Ether experimental program to be complete before we start other things. So we need to start more things in parallel, and we need to do so because quite clearly there will be things which will not work as expected in Ether. I mean, hoping that we build such a huge machine and it just works exactly as foreseen and everything is demonstrated as planned is naive. It's not going to happen. There are going to be things working and things not working. But if we wait until the end of this experimental program, so the second half of the 2030s, before we decide what to do next and what to do in addition to this, we will just wait a lot of time. So we need to build more machines. What is not reasonable is to have a single large installation being built in, let's say, in the Western world. And I know in China is a different thing. They're building something else. But in the West, in Europe and the US, at the moment, what is happening is purely Ether. There is, I understand from your accent that you're British. There is a plan in the UK to build something, and a step is an important installation as well. But as far as I understand, it's not Ether class, and we need more Ether class activities, which means more machines which are in the several billion euros range, which are large, have a lot of instrumentation, and test different aspects. Step, you probably know this, Step is going to test a different type of magnetic configuration, and it should be done. The spherical tokamak configuration should be tested on a large scale. It should be on an Ether scale. Another concept on which there is a lot of attention in Europe is the stellarator. Stellarators should be built, and they should be built at Ether scale. The largest stellarator at the moment in the world is W7X, which is a jet scale machine. And it's very good. I'm not saying that it's useless. It's useful, but there needs to be more of this. And we can afford to have more of these.
Okay, if I may ask, so when you say another ITAR class sort of tokamak, you saying sort of the way the design specification, the physical design specifications of the tokamak are different, so that essentially you cannot test at the current ITAR location because the design specifications are obviously set. So what you're saying, are you suggesting that perhaps a different similar design but different design build needs to be built somewhere to test what is essentially cannot be tested at the current site?
Correct. I mean, ITER was designed with certain objectives. It was designed, well, in fact, it was designed 20 years ago, based on the knowledge which we had 20 years ago. Many new things were discovered in the meanwhile. So I'm sure that if the research community were to design an ITER class machine today, they would not design it in the same way. It would be different aspect ratios, different diverter setups, many different things. But okay, now we have designed it. They have designed it, by the way. The previous generation designed it. Now we build it and we test it and we get the answers. And in the process, we learn. But we can learn other things at the same time, right? Just that we learn one thing and then we look at the next. We can learn many things simultaneously.
Out of interest, could I ask how much you reckon it costs to gather?
I'm sorry, Eric. Can you hold your question just for 1 second, and let's switch to Stefan. He's had his hand up for a little while. We'll come back to you, time permitting, if you don't mind. Stefan, please unmute and ask your question.
I think I'm a bit more optimistic in this regard, because the Commonwealth Fusion Systems is building essentially as a much more tiny tokamak, but of the same kind as ITER is. But it costs just 400 to 500 million US dollars, I know, and has the same target because they exploit the high temperature superconductor magnets we can build since 2015, I think, or so. So it was no path for ITER because this was not invented at that time when ITER was planned, of course. This was no option for ITER, as it was already explained. But there are some 30 companies in the world trying with different paths to build fusion machines now with very different risk levels, I think. But I think the prospects are much better now, because I think the Spark will much be quicker to get ready to do DT experiments than ITER will be, because it's one company and it's much smaller, so it has not the big trouble, and the magnet was already tested. The magnet of a required kind toroidal magnet was already tested before, last year, 21. Sorry. So I think this should be a real option to accelerate things up. Of course, when they will build a real fusion power
Oh,
plant.
I'm so sorry, Stefan. Forgive me for cutting in. We're right about at time, and if you did have a question, it now would really be the perfect time to ask it.
Can I? No, I think it was an interesting comment. Can I answer? Because yes, it's true. HTS is something which was not existing or available. I mean, it was existing, but was not very well established when Ether was designed. So there's no HTS in Ether. Now, when you made the reference to Spark, just for you know for the sake of clarity, Spark is not an Ether class machine. Ether class machine means something which is licensed to operate as a nuclear power plant, as a nuclear installation, which implies not only the tokamak, and a lot of the costs which goes into Ether are not only for the tokamak, they go into the full, let's say, installation required, the hot cell, the remote handling, all the nuclear machinery around it, which is required to operate a device which will generate a high neutron, a high total neutron flux during its operational lifetime. So Spark is an exceptionally interesting machine, but in terms of what it is in the bigger picture, to get to fusion energy is similar to jet. It's a tokamak generating Q whatever, but not being designed as something which could become at a certain moment in time, which could be a blueprint for a fusion power station. That's an important aspect. And then at a certain point, Spark will move to the next step, and probably there will be a Spark 2, which could be then including all of these nuclear regulatory aspects, but it's not at the moment.
Thank you for weighing in on that. Stefan, did you have? We have a couple other hands raised, and Leo, I need to check in with you. We're at time, and I don't want to keep you, but
I can stay, no problem.
Oh, thank you. Okay, cool. We've got a couple other questions. Stefan, I know I cut you off. Did you have a question? Then we need to go back to Eric, and we need to go to Tushar, who's had his hand up too for a while.
Yes, I can ask frankly, how do you think Commonwealth Fusion Systems want to build this fusion power plant called ARC, or have proposed also a little tinier version like called Manta shortly ago? And do you think they can do it in the first half of the 30s, or it's too fast, too demanding for them?
I think a fusion power plant in the 30s is just impossible with whichever technology. I sincerely hope that they will manage to be faster than what, you know, for demo we're looking now at the 40s. So I hope they will be faster than this. I hope, because it's important for all of us that someone gets faster there. But the 30s is tomorrow. The 30s is tomorrow, and honestly, promising a fusion power plants for the 30s is just wishful thinking. It's a very unfortunate and very regrettable situation, but that's where we stand.
Okay, always good to have a dose of frank honesty. Eric, I saw your message in the chat, so we'll take Tushar's question first. And Stefan, thank you so much for those great comments and questions. Tushar, do you want to unmute and ask a quick question?
Hello, ma'am. I'm audible.
Yeah.
Happy New Year to all members, and good evening, afternoon, or morning where you are having what time. My question is, this experiment or this do with those scientists are doing this project. This if the test is succeeded, if they succeeded, then after that, after 2016, then can we build the fusion reactor, I mean fusion power plant, something like the one sunset, in small size, like SUV type, something like that, in future, possible that or not? My question are only this.
So if I understand correctly, you're asking if large size is unavoidable, or if there is a possibility to build a smaller installation, in a
Yes,
nutshell. Okay.
yes.
So I think Stefan was mentioning it. I mean, in between the lines, the size of the magnetic confinement device is essentially scales with the strength, the intensity of the magnetic field that you can obtain. With high temperature superconductor HTS, what we were referring with, it's what is used in many of these more recently designed tokamaks, spheromax, or whatever, I mean, magnetic confinement devices. It's possible to reach higher magnetic field intensity, which means that you can build a smaller machine. Now, there is, of course, a limit to how much smaller you can make the machine. By the way, if you make the machine smaller with the same power output, you have a higher heat load on the wall and on the diverter. And there are technological limits to how much heat you can discharge. So yes, I mean, you can shrink a little bit the size of the tokamak using HTS, but when you do so, at a certain point, you reach the limit which even modern superconductors have in terms of how much current they can carry. But probably even sooner than that, you reach the technological limit of how much thermal load you can take on the internal face of the vessel containing the plasma. So I'm not. I don't think that with magnetic confinement fusion you can get to the point of having a desktop fusion generator, and probably not even an apartment size fusion generator. It can be shrinked, but probably not by one order of magnitude. It's difficult. This is a feeling. It's not. Don't quote me on this, because clearly it's until we build things, we will not see which are the real limiting factors. But that's the view which I think is shared by the magnetic confinement community. With other technologies, it may be possible. If you look at inertial confinement, it may be possible to shrink. Now, the problem there is how do you generate these laser pulses in a compact device, but that could be something to be further explored.
Interesting. And the last technology you just referred to is the one that NIF just, okay, National
Yes.
Ignition Facility. Okay, interesting.
Yeah, I mean, the NIF, I mean, the inertial confinement technology can be shrunk in terms of the power, the power generating core. What would be a challenge in that case would be to shrink the laser beams. But NIF as well is using laser beams which are more than 20 years old. Mm. So laser technology has developed a lot as well. I think there are some private, there are some companies looking at inertial confinement fusion, or even at other type of inertial confinement fusion which do not use laser. Mm. But those using lasers are looking at the development in the field of laser diodes, so laser beam generation, which can be smaller today.
Interesting, very interesting. Well, if you permit, let's wrap up with the very last question. I guess a succinct question from Eric. If you still have your hand raised, or
Sure, if that's right. Thank you. I think it might have been answered potentially, but I'll just ask it and sort of perhaps expand a tiny bit. So I know you mentioned about the designs obviously will change, and they obviously have changed again since clearly again in 2015 with, I think it was the ARC, I think Stephen suggested, for about 500 million US dollars. I suppose the question is then, if one was to be able to find funding or get funding for a new design, how much do you reckon it would cost to design one with the latest technology, 7 years after 2015, or 8 years, I suppose? How much do you think it would cost to actually design one today with the latest technology, having not designed one before?
Honestly, I don't know. What I can tell you is that, well, I don't know for many reasons. It's not. One thing is that we do not see, as the European contribution, we do not see the full cost of ITER, and we see the European cost. We don't know. Well, there is some transparency about what is spent in the US, so we see what is spent in the US, but we don't know what is spent in China or Russia, and also very little about what is spent in India for their part. So there are only estimates about how much ITER costs as a whole. When I look at what we're spending for the European components, I would say that just addressing the organizational difficulties, not changing technology, just the organizational difficulties, which cause delays and cause, reworking, we could probably cut the cost for ITER in half.
Yeah.
So as an order of magnitude, I think half of the money which we're spending is not strictly necessary to build the component, which is also one reason why the initial cost estimates were much lower than what we're spending, because the initial cost estimates never really took into account these organizational difficulties. Or project management, sometimes you refer to these as project management difficulties. I prefer to use the expression organizational because it's not only project management. There are many different types of organizational difficulties which we face.
Mm.
Now, if you start factoring in other technologies, and for example, if you start imagining building components rather than using 20th century technology, most of the components are, cut and weld. That's how we build. That's how it was designed. That's how the nuclear regulator requires the components to be built. So if we could use, for instance, additive technologies, 3D printing on a large scale to build some of the components, there are some studies, and it's not completely science fiction. There are some experiments, some tests. Probably we could reduce even further. The problem we have with laser printing, for instance, of structural components is that the nuclear regulator is not, at this moment in time, ready to consider. Take, for example, a pressure vessel. They're not ready to consider a pressure vessel which is built in a way different than the conventional cut and weld approach, which is well known. There are some manufacturing codes, so you know how to build it. And that's what the nuclear regulator sets, and that's how we build.
Okay. Thank you very much, Steve. Appreciate it. Cheers.
Leo, thank you so much. Obviously, you're a fountain of all kinds of great information on the technology side, on the organizational side, on the financial side. We could do a master class with you, and I feel like that's what this has been. But I know we're definitely way over time. You've spent an extra 15 minutes answering questions, so I that's very generous of you. Thank you very, very much, everybody, especially to Leo for giving us this presentation, and for everybody for attending. I think we're gonna have to, I think we're gonna have to wrap it up here. Leo shared his email address on the slide, so I'm sure he welcomes you contacting him. Is there anything that you'd like to leave us with? I'll let you have the last word, Leo. Thank you so much.
No, there are no last words. And I think, as you mentioned, I remain available if you want to continue these discussions offline by email or even talking. It's interesting. I mean, it's clear that we are at a kind of turning point with fusion, and all of these private undertakings are changing radically the scenario. And to me, the question is how. Oh, someone is. I will put my email address in the chat. Someone's asking me. The question is how we make sure that these two different sides of the development really work with synergy. There's no competition. Actually, the public research community is very happy and excited to see the private undertaking, all of these startups, because it really allows to test things which have been discussed for ages, but for which there was never public funding available. It really allows for things to be tested quickly. And this question about high temperature superconductors, it's essential. How would it work in practice? How will it, once you design a machine having access to this, how does it work in practice? Nobody has much of an answer to this. You know that existing superconducting tokamaks are relatively small. JT60, which is the largest superconducting tokamaks, is not using HTS, is using conventional low temperature superconductors. So that the curiosity is there in the whole community, and the fact that there is someone else trying and testing these different views is really very exciting also for the public side of the debate. We need to find a way to have these two communities working together effectively, efficiently, because in the end, I think the ultimate goal for everybody is to get to a source of energy which is answering the energy and climate crisis we have at the moment. At the moment, we also have an energy crisis. In Europe, it's very much felt.
Those are some very inspirational thoughts to leave us with. You've got my mind going now. Everybody, thank you so very much. And Leo, thank you so very much. Thank you for your generosity and your willingness to take questions from people, and now to even, continue the dialogue offline. So, so let's continue this. This is just the start.
Thank you indeed for giving me the opportunity, for organizing this session. Thank you to everybody who attended, and thank you for the interesting questions.
Bye-bye, everybody. Bye-bye. Happy New Year. Bye-bye.
Bye-bye.
Bye-bye. Thank you so much. Yes.